Hello, everyone, and welcome to the Parsons Technical Webinar Series. I'll be your host today, Jessica Bennett. Today we have with us Hannah Annunziata and Jim Schutz presenting on innovative pilot testing for bioremediation of chlorinated volatile organic compounds in overburden and metamorphic bedrock groundwater. We'll go through a few housekeeping items first on the next slide. We'll be keeping all phone lines muted until the Q&A session at the end. If you have any questions during the webinar, you can enter them into the Q&A section at any time or hold them until the end to either post in the Q&A section or you can raise your hand and ask your question live. This webinar has been approved for 1 professional development hour or PDH credit. If you'd like to receive a PDH certificate, a link to the attendance form is in the Q&A section. There are 3 multiple choice questions you'll need to answer, so please take a look at those. If you have any issues accessing that form, the questions and multiple choice answers are also posted in the Q&A section. And if you have any issues regarding the PDH form, you can send us an email at daniela.sabin@parsons.com. We will be issuing any requested PDH certificates in about a week. And finally, this webinar is being recorded and will be posted on our YouTube channel in the next week or so. So just a brief agenda, we'll introduce our guest speakers today, followed by a core value moment before we get into the technical presentation and then wrap up at the end with Q&A. So a little bit about our presenters. Hannah is a geologist specializing in contaminant fate and transport. She has 7 years of experience with a focus on the mechanisms that affect PFAS and CVOC fate and transport, as well as one-dimensional fate and transport modeling. Hannah's involved in the Parsons internal R&D program working on emerging contaminants, and she also supports environmental investigation and remediation projects for clients. Jim is a principal hydrogeologist and technical director of environmental geological services here at Parsons. He has over 24 years of experience specializing in groundwater modeling, investigation, and remediation of sites in complicated geological environments. He earned his BS and MS from the University of Buffalo, and he's a PG in New York and Pennsylvania. And with that, I will hand it off to Hannah for the core value moment.
Thank you for the introduction. So for today, I wanted to focus on a core value that was relevant to some of the field work for this project. So I will focus on a safety moment. Next slide. So specifically for this project, we had to work near water, and so several of our wells were located within a lake, and we wanted to make sure that our field team had the proper PPE for this activity. This included waders, a personal flotation device, as well as a secondary device, in this case a throw rope, which was held by someone along the shore to assist in case of an emergency. Next slide. So next, I will go over just basically the overview of the content that we will discuss today. First, I'll provide a background on the site setting and historic investigations, as well as a little background on the CVOCs. And then I'll hand it over to Jim, who will discuss the bedrock hydrogeological investigations at the site. And then we'll talk about the 2022 groundwater conceptual site model that was developed, which led to the work for the implementation of pilot studies, as well as our conclusions of this work and next steps for this project. Next slide. So first, for the site background and conceptual site model. The site setting is a 400+ acre Resource Conservation and Recovery Act facility in the Northeast United States. For this particular project, this is one area of concern, which is highlighted with the blue polygon at the northern extent of the larger RECRA facility, where scrap paraffin wax and drum wastes were disposed. Next slide. So specifically for the larger site, there are RECRA corrective measures that are required to address contamination in lake sediment, soil, and groundwater. For this presentation and the work for this project, it is specific to the groundwater. And it is important to note, though, that for the lake sediment remediation, this activity was completed in 2022. This figure here does show when the lake was drained for that sediment remediation. And so because of that, the design for our 2023 investigation and pilot activity, the design being protective of the lake was an important aspect of the design. Next slide. So for the site investigations, there have been over 30 years of investigations at the site dating back to 1990. From these investigations, the primary compounds of concern that were identified were tetrachloroethene, PCE, trichloroethene, TCE, cis-1,2-dichloroethene, CDCE, and vinyl chloride, VC. For this particular area, there are no buildings or structures, and the area will remain open, so there's no vapor intrusion risk. Additionally, in this area, the groundwater classification and availability of public water leads to us using the state surface water protection criteria as our target cleanup standards for the groundwater. Additionally, through the prior investigations, there have been interim measures performed at the site. Specifically, 2012 through 2019, there were several excavations and drum disposals, as well as groundwater sampling. This picture on the slide is the most recent excavation from 2019, which was performed after dense non-aqueous phase liquid DNAPL was found in a monitoring well. I also wanted to highlight this excavation activity, as the 2019 excavation area was the focus of our pilot study, which we'll talk about more later on. In total, over 5,500 cubic yards of soil and over 200 drums were excavated as part of these interim measures. Next slide. So now for a quick background on chlorinated organic compounds. Just quickly, I wanted to note that these graphics here are for educational purposes, and they are not a depiction of the site. So chlorinated solvents, the CVOCs at the site, as I mentioned, they are DNAPL. And so here, this image is depicting some of the fate and transport mechanisms that control DNAPL in the subsurface. A note, DNAPL being denser than water, it will sink to the bottom of aquifers, and then that gravity does dictate some of its transport mechanisms. Also, the reason that these products are widespread is due to their ability to dissolve organic materials. So their applications include industrial degreasing, dry cleaning, raw material for manufacturing, and metal fabrication. So in the environment, some mechanisms that control their fate and transport include volatilization, biodegradation, sorption, dispersion, and dilution. For this project, we are focused on the biodegradation and natural attenuation aspect of fate and transport. Natural attenuation can be kind of a bulk parameter that includes biodegradation, as well as other mechanisms that will contain the mass. But yeah, as I said, we'll focus on biodegradation, which I have more info on the next slide on. So specifically, there are a variety of abiotic and biotic degradation pathways for the CVOCs. For this work, though, the primary microbial reductive dechlorination pathway we're targeting is highlighted on the right of the slide. And this is the process in which the parent compounds, PCE and TCE, are sequentially dechlorinated to the non-toxic end product ethene in this case. And additionally, here I've highlighted a few of the microbial species that are important for these processes. So that's kind of my quick overview to some of the important fate and transport mechanisms. And now I will hand it over to Jim to discuss some of our subsurface conditions at the site.
Hannah. All right, so as this slide shows here, we have overburden, weathered bedrock, and competent bedrock. There's 0 to 30 feet of overburden above bedrock, and I think that's important, and has been important in our implementation of bioremediation, particularly because in some cases the overburden is very thin. That 0 is a real number in the fact that some bedrock outcrops in the vicinity of the area of interest, as well as adjacent to the areas that we were injecting. The overburden is impacted with VOCs, as Hannah noted, most particularly chlorinated solvents. The concentrations in overburden generally decrease with depth, but we did identify a need for bedrock investigation as will be explained a bit more. And here you can see the overburden, weathered bedrock, and competent rock in a cross section that's really, in this case, parallel to the shoreline. So the bedrock at the site is a gneiss, essentially, which is a very dense and hard metamorphic rock. And if you don't know, metamorphic rocks are crystallized, so they're a crystalline rock, meaning the crystals are have formed the fabric of the rock that are tight and connect without very much pore space at all. So the pictures here really identify what the bedrock looks like, in particular, like right adjacent to the site. So you can see how this bedrock outcrops. You have these large phenocrysts. These are plagioclase with finer grained crystals sort of surrounding them. The important point of this is a lot of times we talk about fractured and weathered rock, and we have a certain depiction of our mind of it being sometimes crumbly, or think of a shale, and it's just falling apart. It's almost a soil. You may have worked in saprolites where it's a gradation from soil to very weathered rock to less weathered rock to competent rock. In this case, and particularly related to glaciation in the Northeast. If you're from the Northeast, particularly the New England area, there's a lot of metamorphic and igneous rocks. And then the glaciers came by, 20,000 years ago, scraped a lot of the weathered overburden off and kind of left a cleaner bedrock surface after the glaciers retreated. Soil developed and was deposited on top of the rock. But oftentimes in the Northeast, we see a very, very specific contact to top of rock. And in this case, the bedrock is very competent. And you also get a picture of, or a depiction here of, how very little fracturing there is. And that very little fracturing leads to very, very low hydraulic conductivity, and even from a relative perspective, lower storage coefficient. So storage coefficient is important, as well as porosity, in terms of how much water is entrained in the rock. How much do we actually need to remediate it? What's the volume? Continue on here. So there was a deep well at the site, and by deep I mean about 120 feet. And we noticed, we made some observations about concentrations in that well, and we thought about it from basically identified that there was a need for additional identification of fractures in that deeper open borehole. So it's open borehole from about 35 to 120 feet deep. So on this slide here, this is the well that we're talking about, this 48R. There were 2 fractures identified, really only 2 fractures identified in the geophysics. It was open borehole down to 120 feet. A flute liner was used. So that's that flute liner that sort of unrolls like a sock and protects intermingling of groundwater. We it was identified that on the flute liner there was some high concentrations of VOCs. The flute liner, the version of the flute liner used here is one that can, identify if VOCs are in the groundwater. And sure enough, some VOCs were identified at depth, which made us sort of wonder, well, if there's no fractures down there, how did the concentrations get to that depth? Is there an actually water-bearing zone? So that's kind of summed up here in these observations. Shallow weather bedrock not present at this borehole, very competent all the way from top to bottom. No water-bearing fractures below 15.6 feet in elevation based on core geophysics. There was no visual evidence at Napple at the base of the boring, and the well based on the gauging. However, CVOC concentrations on the flute liner. So to expand on that point a bit more, here you have some images of the flute liner. There was some minor staining. It was sampled for VOCs at the deeper elevation where you can see the staining here. It's 123 to 125 feet and 20 to 22 feet. There was an increase in PCE and TCE with depth. And we started to hypothesize, okay, if there's no water-bearing zone, how did these concentrations get there? And we developed a conceptual model that maybe it was related to the installation of the flute liner itself, an artifact of the borehole conditions. So this next slide here is a very basic graphic depiction of how we thought about this. So the purple blob here is my simple depiction of the groundwater concentrations as they exist. The vertical lines are the open borehole, and then you have a fracture, and this is, let's say, at the 40 feet below ground surface. So you have your concentrations kind of like going through the borehole and spreading and dispersing a little bit up and a little bit down from that borehole. The way the flute liner is installed in very low hydraulic conductivity boreholes, especially as the hydraulic conductivity decreases with depth, is you put a tube down to the bottom, you start pumping out of the top, and the flute liner slowly moves down. And what we hypothesized and wanted to test was, okay, if the flute liner potentially pushed the concentrations to the bottom, resulting in the absorption of the concentrations, more so at the bottom of the flute liner, where there was time for them to contact and absorb, and therefore that could be the reason for the concentrations at depth. Existence of a water-bearing zone. So what we set forth to do is test the well with what's called a fluid replacement test. We do these tests a lot in fractured bedrock. They're kind of cool. They're a lot of fun. And I'll explain how this looks in a borehole. So again, very basic depiction here. Blue is the water column in a well. There's a casing, which is the gray transparent color at the top. So you pump water out of the well and you pump a tracer into the well at the exact same time at the exact same flow rate. And what happens is within this borehole, you replace the well fluid, i.e. the groundwater that is in the well, with a tracer. And you keep your flow rates pretty much identical so that you don't have head building up and pushing tracer out into the formation, or you're not pumping too much out and drawing the head down and sort of diluting your tracer as you go. And slowly over time, you end up replacing all the well water with the tracer itself. And then your tracer test essentially begins. So a little more on how this looks in the borehole itself. On the left-hand side, you'll see we have our tracer. It's replaced the water. That's why it's light green. Got a little bit of stagnant water at the top that's up in the casing. That's not a big deal. And you have a conductivity probe and a fracture. And So what you do is you start moving this conductivity probe, which is this dark blue rectangle. You start moving it up and down in the borehole. And as you move it up and down in the borehole, you produce conductivity logs. So this is a conductivity probe. We like the one that has head and conductivity measured in it. And as you do this, you get different successive runs of conductivity as water is starting to migrate into the borehole from the fracture itself. So as the clean groundwater is coming in, clean, i.e. doesn't have the tracer in it, so it's of lower specific conductance, it starts to move through the borehole, and you can see each one of these are a successive log where the red was an early time as the tracer started to migrate into the borehole. The green is a little bit later time, and then by the time of the end of the test, you have this nice big peak, which shows, hey, we have a fracture up in the top. Meanwhile, there's no action at the bottom. There's no kicks on the conductivity log, and therefore no flow in the borehole. So that's the hypothetical of how the test is run to demonstrate some of the actual results here. We have test one, it was static, so there's no flow into the borehole. One thing, when you have a very low stress it, you got to pump it out a little bit. And so that's what we did here. We actively pumped, and then we started seeing clean non-tracer groundwater coming into the borehole at the depths where we identified fractures in geophysics. And sure enough, there were no kicks at depth, indicating that there is no permeable fractures, and i.e. very, 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 very low hydraulic conductivity throughout most of the borehole. So a summary of these investigations: geophysics results showed that there's no evidence of groundwater flow below 35 and 39 feet. The flute fact liner indicated there were CVOCs at depth. Additional investigation was necessary. The results of the bore fluid replacement test were that there was no migration, no deep migration pathway. And then we were able to partially abandon 48R to really focus right in on those fractures that are relative to groundwater flow, as well as the remediation.
So now to kind of shift gears back to our COCs, some other aspects of our hydrogeologic investigation as part of this groundwater conceptual site model was looking at some trends in overburden as well. So here's a map of our site, and the blue arrows indicate our general groundwater flow directions. And here also highlighted is the 2019 excavation area, which is the purple polygon, again highlighting a likely historical source area for contamination. So next, some more concentration trends. Mostly throughout the site, locations have decreasing total CVOC concentrations. So here's a few time trend charts, and as well on the map itself, locations that have the green circles represent the locations where there is this decreasing trend. And additionally, in the western area of the peninsula, this decreasing trend we did not notice. In this area, concentrations were more stable over time, which again happens to coincide with that area of the 2019 excavation area. So this was kind of our general observations we've made related to our concentrations of our CVOCs over time. Next slide. So next we wanted to look at this data in terms of natural attenuation. So some additional lines of evidence that we looked at to determine if natural attenuation may be occurring was if degradation products are present, which they are, the geochemical conditions were moderate for natural attenuation to occur. And specifically for biodegradation, the appropriate microorganisms exist at moderate levels based on our qPCR analysis. Something else we noticed was that the decreases in CVOCs was increased at locations where there were either detections of total organic carbon or historical hydrocarbons that were present. So based on this natural attenuation evidence evaluation, as well as the data from the previous slide where we looked at our concentrations, it did appear that natural CVOC biodegradation was occurring in most areas of the site. So based on this, the conclusions of our 2022 groundwater conceptual site model were to evaluate 2 remedial actions at the site. Firstly, monitored natural attenuation, M&A. So the shallow sources at the site have been removed. Overall, there's a decreasing overburden groundwater total CVOC concentrations. Natural CVOC biodegradation is occurring based on the multiple lines of evidence that we looked at, and there's an absence of a deep bedrock migration pathway. Additionally, we wanted to look at enhanced in situ biodegradation, EISB, in that western part of the peninsula around the 2019 excavation area due to the stable trends in total CVOC concentrations. And additionally, that part of the site did have lower or non-detect organic carbon concentrations, indicating that while the native bacterial populations are capable of completing biodegradation to the non-toxic end product, they may have ran out of their carbon source. So for our M&A and EISB pilot test activities, these occurred from 2023 to 2025. The pilot tests were performed as part of RECRA corrective measures study to identify and evaluate potential remedial alternatives of CVOCs in groundwater. There were 2 site-wide M&A events, and as part of the EISB pilot test activities, 14 injection wells and 4 additional overburden monitoring wells were installed in the EISB pilot test area. Due to the proximity to the lake, we wanted to, again, make sure we were being protective of the lake. And so to prevent daylighting into the lake, we only injected into the first row, the up-gradient row of injection wells, which we'll show on a later slide. And for the actual monitoring portion of our EISB activities, we had one baseline event as well as 5 additional quarterly monitoring events. So we had several objectives for both our M&A and EISB projects. The M&A program was primarily to confirm some of our prior observations, this being to confirm that the overburden CVOC concentrations are decreasing, confirm that the degradation products are present, also evaluate if there is a complete biodegradation pathway to ethene, and document that the appropriate geochemical conditions and microorganisms are present. For EISB, we wanted to develop a sustainable approach for treatment of CVOCs in groundwater, determine the feasibility of EISB to reduce CVOC concentrations to the extent practicable, while also being protective of the lake, determine the optimal design parameters, and test the ability to treat bedrock through overburden treatments.
And if I can just interject here, yeah, this image on the right-hand side is pretty cool, and I just wanted to point it out. We had a very nice injection system with this header, flow meters on everything, just everything gauged and all built in the field. And a shout out to Jim Shaw, who really spearheaded a lot of this on-site injection equipment construction.
Thanks, Jim.
Yeah, back to you.
So now, for this next slide, I just wanted to kind of introduce our pilot test injection area. So again, the focus was this 2019 excavation area. And here we're showing our series of injection wells and monitoring wells throughout the area. And this also kind of highlights how there were more up gradient wells and then down gradient wells. Down gradient being the locations closer to the lake. Next slide. And again, to kind of highlight the actual injections, this is a view showing our injection area, the size of the injection area, and we can see to the left where that injection apparatus and our substrate staging area was, as well as our tubing, which connected to our injection wells. And the other thing I wanted to highlight from this slide is the location of our monitoring wells. So we had monitoring wells nearby to our injection wells, which we used in the field to monitor for substrate breakthrough. So we had some transducers deployed, as well as using balers to collect samples for visual observations of breakthrough. Next slide.
Can you hear me?
Yes.
Okay.
Now I
I
can
was just
hear
going to point out, this really does give a good idea of the scale of the project area. Sometimes in maps, it can be a little bit misleading about the size of the project. So pretty tight area, which really came into play on how we installed our wells, how we phased things, and how we were able to kind of use just one of the injection lines instead of both in order to, really avoid having any daylighting out into the lake. Back to you.
Thanks, Jim. So we did monitor for substrate breakthrough, and this was again to ensure that we were achieving the radius of influence that we wanted, as well as making sure that our substrate wasn't traveling too far and getting too close to the lake. So this is an example of a treatment area overburden well where a transducer was deployed, and the peaks represent where there was substrate breakthrough. This was based on the specific conductance. So the substrate had a high specific conductance relative to the groundwater. So the increases in tandem with the changes in the groundwater elevation were representative of breakthrough. And this also coincided with our visual observations, which we have shown in the picture, where our samples that we were taking over time of the groundwater became increasingly cloudy, representative of the substrate reaching those wells.
And one thing to note as well, we like to use these real-time probes when we're doing our injections. I know, in the past, oftentimes folks, in Parsons, we've done this as well, where you just purge out the water of the well until you start to see substrate. What we found, and we've published in previous publishings, is that if you're not looking at specific conductance, you have a chance that you're going to underdose your substrate, and that's why we really like to use these inexpensive but cost-effective specific conductance probes, so then you can see the substrate starting to show up, and it complements the visual effect here. So, for example, the writing on the jars are time, and you notice all the way on the right-hand side, that's what's in the mix tank. When you get early time here, at T1200, you're getting some of the substrate, but because of that dispersive front, longitudinal dispersion, right? As opposed to transverse, there's a little of both, but you're getting that longitudinal dispersion, and the injectate is spreading out in forward motion of flow. And so you start to see the substrate and you think to yourself, okay, we're good, we can shut off our pumps, but really you have not achieved the higher concentrations of the substrate. And all our designs are very specific to how much loading do we want, what's the concentration of the EVO, emulsified vegetable oil, how much hydrogen is that going to produce compared to how much mass we have to treat in the aquifer. So all this design is very specific to, okay, dose it correctly, have longevity of your substrate so that you can reduce the full mass. But if you cut your injection short, you've just only provided half or 3/4 of the substrate, i.e. the hydrogen that you need. So I think that's important to just kind of highlight, and I'll give it back to you, Hannah. Sorry, I keep interjecting, but I think there's value in
Thanks.
there.
Yeah, definitely valuable points that are made. So I appreciate it. And in terms of the longevity of the substrate, after the initial injections, we did return post-injection for monitoring of our geochemical conditions. So this was based on some samples collected throughout our injection area, not just our wells that we injected into. So we monitored for several field parameters, including dissolved oxygen, pH, and oxidation reduction potential. We also bailed wells for visualization of that milky appearance, collected samples for TOC, as well as dye traps for analysis. So our substrate injection, we also had fluorescein dye as a tracer. So the dye traps were deployed at wells throughout our injection area, and we did detect the fluorescein dye at locations throughout our injection area, indicating that there was some influence of our injections throughout our targeted area. And this was also supported by those initial TOC samples and the geochemical conditions. So based on the substrate observations in our down gradient injection wells, the geochemical conditions were appropriate for culture injection. So we did bioaugmentation with the KB1 plus culture at all 14 of our injection wells to kind of jumpstart that biodegradation process. So now I will discuss the actual results of our pilot test. So first, these are box and whisker plots showing our baseline data and our 5 subsequent monitoring events for our parent compounds and our daughter products. So the top are our parent products, PCE and TCE, and we can see pretty quickly that first quarter monitoring event, we have really large decreases in our concentrations, and those concentrations stay low throughout our monitoring period. For CDCE, that is a daughter product. So while there is an initial increase, that's not unexpected, as the parent compounds are transforming into CDCE before then being degraded. But we are seeing decreases in our CDCE concentrations. And similarly for vinyl chloride, we do see increases in that from the transformation of the other compounds into vinyl chloride. However, the last couple events, that increasing trend appeared to start to stabilize. But the really promising results was our really large increases in ethene and ethane that we observed, showing that we were able to have this degradation process reach the non-toxic end product. So that last slide showed the summary of data, and now to kind of focus on some of our primary monitoring locations. Firstly, this is a close-up of that injection area. So that blue arrow represented our localized groundwater flow, which in this case is to the west towards the lake. These 4 locations highlighted were our primary injection wells, and the 2 starred locations represent our monitoring wells, where we had observed breakthrough in the field from that live monitoring of substrate. So based on where we injected our mass, groundwater flow, and where breakthrough was observed, we wanted to focus on this series of wells as our primary area of influence, first starting with where breakthrough was observed and then looking at locations down gradient. So here we'll look firstly at our CVOC trends to look at our primary line of evidence of biodegradation. So as shown in the box and whisker plots, we are seeing good decreases in our parent compounds, especially at our location with substrate breakthrough and the location slightly down gradient. We also see the corresponding increases in our daughter products, including ethene at these locations. Further down gradient at our locations that are closer and within the lake, we also are seeing the similar trends with decreases in parent compounds and increases in our daughter products. However, that location that's furthest down gradient, we are seeing less of an impact. We're not really seeing much changes in our CVOC trends. Next slide. So to look at some of our other lines of evidence for biodegradation, we also looked at our microbial analyses. So for this presentation, we'll highlight the D. halicoides data. So D. halicoides was part of the KB1 plus culture that was bio-augmented. So we wanted to really focus on that particular species as we knew it was injected, and we were hoping to see increases in those concentrations. And at our locations within our pilot test area, we do see really good increases in the cell counts of the D. halicoides compared from baseline to the end of our monitoring period. At our locations, though, that are further away from our injections, we see less of an influence. And at our furthest down gradient location, we're really not seeing any signs of D. halicoides increases from our bioaugmentation. So next, for our total organic carbon, TOC, again, looking at these same monitoring wells, we saw really good increases in our TOC concentrations at our locations within our pilot test area. And then the bottom row shows those locations further away where we're seeing less of a change in our TOC concentration. The other notable thing with our TOC data is that our TOC concentrations are sustained. So again, really thinking about that longevity impact of our injections. We're not seeing, at least through our initial 5-quarter monitoring period, that the carbon was being used up. So that was really promising to see.
Yeah, and for most of our bioremediation projects, we want to keep the TOC, 30, 50, somewhere above those concentrations in milligrams per liter. And as Hannah pointed out, when we got above 100 and really hovering at or above 100, right in the area of the higher concentrations and where we were trying to treat, that TOC concentration trend increased even down gradient. So we're seeing down gradient effects of the source area treatment, which is exactly what we're trying to achieve in not only lateral distance, but also depth. So that's one of the things that's important to note about the elevated TOC concentrations.
So next, we'll discuss some of our bedrock data to again look at that vertical impact of our substrate injections. And here I'll hand it over back to Jim to discuss our bedrock data.
Yeah, thanks. So the area that we're really thinking mostly about in terms of high concentrations of CVOCs in the bedrock, our center ground, the southern part of the previous excavation, where we have MW48R, MW48D, and MW49. And as a reminder, that 48R is now RA because we've closed off the bottom of that well and we're focusing really on that one fracture itself. So as a look at how the CVOC trends are in bedrock, it's important to note that we do have relatively low mass and overburden. And the concentrations at 48D are dominated by total CVOCs, is dominated by PCE, and 48RA is dominated by cis-DCE. So that gives us indication of dechlorination with depth, with the primary concentrations being higher in 48D of dominated by DCE at depth. So it looks like, just like you would expect spatially, we have that dechlorination profile vertically as we go from overburden into weathered top of rock and then down into these two overburden fractures. These are micromoles. So you notice the scale bar between 48D, 48RA, and 49, the overburden, is just a lot lower in concentration, as noted up here. One thing that's been sort of interesting and something that we've been watching and thinking about is the concentrations in this 48R have continued to decline very steadily. And while we don't see a lot of indication that the TOC is migrating into those upper fractures, was maybe a direct result of our bioremediation in the overburden. Now, there's two factors involved in this, as you should remember from this slide deck, is that we did close off the bottom of that well. So we're trying to, think about two parameters at once and what's the cause and effect of these concentrations dropping over time. And for the EISB conclusions, we completed the pilot test of the EISB injections and they were successfully implemented. As with any pilot test, we really learned a lot. I remember, Hannah was out in the field installing wells and calling me back in the office because there were some very shallow top of rock zones. And we're like, hey, what do we do here? What do we do there? And so as the whole purpose of a pilot test it's to learn something. So we're able to use our dynamic work plan written with flexibility in it such that we could make those field calls and say, okay, top of rock, it's above the water table at this one location. Let's not install a well there. That doesn't make any sense. Let's move over to where top of rock is deeper. And the site had a good good mapping of the top of rock, so that was very useful in our sort of small subtle changes to the where we located wells because of the undulating top of rock surface, which is another important point about the difference between sedimentary rock and metamorphic and igneous rocks. You often have a very uneven surface in metamorphic and volcanic regimes, as you probably noticed in one of the earlier photos where the excavation just followed that undulating rock surface. And it might be 2 feet below ground surface in one spot and then 6 feet 2 feet away in the lateral direction. We saw strong evidence of full biodegradation to ethene at primary locations within the primary zone of influence of the injections. That's one of the most important factors in our tracking of these concentrations. You want to see the primary compounds degrade. Obviously, you want to see everything degrade, but in the interim, while you're waiting for more data and the biological system to continue to do its job, that ethene production is an indication that even though you may have vinyl chloride or cis that is staying steady, as long as you're still producing ethene, and I think of this biodegradation as somewhat of like a conveyor belt where things are continually moving and more ethene is being generated, meaning we're still good. The system is still doing everything it needs to, because ethane are very light volatile compounds, so they're not going to last. So as long as their concentrations are staying high, that means we're continually reducing the primary compounds to the degradation products and to ethene and ethane. This was supported by trends in CVOCs, microbial populations, TOC, and other geochemical conditions at all of our bioremediation sites and our natural attenuation sites. We spend a lot of time thinking about, not only the concentrations of the CVOCs, but the microbial populations, the TOC, and other geochemical parameters. Locations further down gradient, side gradient show some slower degradation, and bedrock shows some potential minor indirect influences from injections. The W48RA shows a strong decreasing trend. 48D shows some evidence, some decreases in PCE and generation assist, and that's likely from the remediation that's happening above. So site-wide M&A trends, upgradient into the pilot test area. Here you can see these box and whisker plots again. So this shows all wells in one box and whisker, and you can see increases and then decreases even before the bioremediation happened, probably related to the excavation that we talked about in 2019, and they continued to decrease over time. And so it's important to note, even on some of these bigger ones, you know, the X is the mean, the line is the median. So when those two are separated, that means you know, you have a skewness to your data set. So we really just had a couple of concentrations that are very high, but those have continued to drop off, and the mean and the median have approached each other. And concentrations are below the surface water criteria and stable over time. TOC and microbial population cell counts are low, but so is total CVOC mass. And side gradient of injection area. So here we have some locations that are side gradient of the injection area. In some cases, we do have some decreases, but PCE and TCE is still above the surface water criteria. And these wells were very specifically outside of the pilot test area. We injected here. We're talking about these locations up here. So we did our pilot test here. Now we're thinking about, okay, we have these wells that are, some of the concentrations are lingering. What are we going to do about that? Because there's not much ethane and there's little to no TOC. And that's where we come to our next steps. So conclusions and next steps. We're recommending that two remedies be carried out at different areas of the site as part of the RECR CMI. Then the final remedial design is in progress. Continue with M&A in the Eastern Peninsula, particularly in the areas outside of our injection areas. You know, we think about monitored natural attenuation in time and space. So it's always part of a remedy, particularly on the fringes of the plume where you might not need to treat, but it becomes more a part of the remediation as you work through the more active remedial implementations such as bioremediation. And then secondly, additional injections where stable PCE and TCE trends remain, farther gradient and side gradient in the pilot test area. Eventually will be transitioned to M&A after successful treatment with EISB. And then within the pilot test area, potential injections into weathered rock and or fractures as part of the remedial design. So we recognize we need to be a little more aggressive and probably need to be a little bit more aggressive in bedrock. And so we're kind of thinking about how to increase the remedial progress in the shallow fractures of the bedrock. You're nothing without your team. So a special shout out to many of the contributors here. And there's a long list of them. So I'll just let you read because you probably know some folks on this list. And time for questions.
Yeah, thank you, Hannah and Jim. That was a great presentation on implementing a pilot study in what sounds like some pretty complex hydrogeological conditions and some key considerations. If anybody has a question, you can put it into the Q&A section instead of the chat feature, which has been disabled. You can just post it there like normal, and we can read it out, or you can raise your hand and we'll call on you live. And I thought I saw a hand raised, but hold on.
Yeah, Ed Heisey's got his hand raised. He raised it again. Hey, Ed.
One second.
Unmute.
All right, you should be able to unmute now.
Hi, Jim. Thanks for the presentation. Two questions for you. What substrate were you injecting?
So an EDO and emulsified vegetable oil.
Okay.
Yeah, purchased from a vendor.
Okay. Did you notice any issues with controlling pH?
We didn't have too much of a pH drop. Hannah, you probably remember, did we mix in
Yes, we did add bicarbonate for a buffer. Yeah. And because we did our baseline conditions also were a little below your optimal level for biodegradation. But yeah, our pH was pretty well maintained at, I would say, mid sixes.
Yeah, so we did the sodium bicarbonate. Did we also use that calcium carbonate buffer that you can mix in? It sort of has a longer
Yes.
buffering capacity. Okay, so
Yeah.
we use two.
Okay.
Thanks, Adam.
Thank you.
And there's a question from Hudson. Are there any subsurface conditions that we need to monitor and that would inhibit or destroy the microbiome, which is degrading the CVOCs? So that's similar to Ed's question. That's where he was going. We do have to monitor certain things, particularly pH. So as the bioremediation process happens, you produce hydrogen, which is an electron acceptor or electron donor. I forget, Aaron, you can probably correct me. I always flip those around. But you add the organics degrade, they produce hydrogen. That hydrogen then allows for the microbes to transfer the hydrogen and pluck off one of the chlorines and plop on the hydrogen. That's the sequential dechlorination process. And in doing that, what is free hydrogen? It's the measure of pH. So you're producing all that hydrogen, you're dropping your pH. And if you get below, 6, it's kind of like a cutoff that's thrown around. You don't really kill off the biology. They just sort of go dormant, but you can see a stall in your system. Another thing that we watch for is hydrogen sulfide production. So some sites where we've treated, for example, a dolomite, the dolomite is very iron limited, so there's not a lot of iron in this whole process. If you're reducing sulfate, which you want to do, you want to make your anaerobic system into a sulfate reducing condition. That sulfate reduction can combine with the hydrogen and produce hydrogen sulfide. Hydrogen sulfide is also toxic to biology. Most of the time, if you have enough free iron, the hydrogen sulfide doesn't last, and the sulfides bind with the iron, produce iron sulfides. So in this case, it was a sandy aquifer, so we weren't really too worried about hydrogen sulfide. But those are the two that we probably spend most of the time thinking about. In some colder climates, you can actually be inhibited by just lower temperature in the aquifer, like if you're up in the Arctic or something.
I just wanted to add as well, not necessarily specific to inhibiting the microbiome, but some other geochemical conditions we monitored that we didn't really talk too much about in the presentation were our sulfate concentrations, our dissolved iron concentrations, and ORP, methane, other indicators that can kind of tell you about the geochemical conditions. So, you want to have reducing conditions, so a really negative ORP. In our case, we saw decreasing sulfate concentrations, indicating there was probably some sulfate reduction happening. And methane is also usually associated with biodegradation. So sometimes you'll see increases in your methane before you see the actual biodegradation of your target compounds.
Yeah, good point, Hannah. Thank you. Some other questions that are sitting in this chat. I guess we'll start from the bottom. We just covered Hudson's. Dana VTech. Hi, Dana. What would you like to modify in the full-scale position compared to the pilot study? We've been throwing around some ideas of maybe a bioreactor or some injection trenches because, the water table is pretty shallow. So having injection wells, we might be able to control and inject more pervasively if we use a different type of approach. So we are kind of thinking about some of that. Laura Morgan, hi Laura. What are some of the challenges that you encountered in the injections we were able to overcome? We did have daylight. So daylight is you're injecting under low pressure, but somewhere up to 5-10 psi in these wells. You don't have a lot of freeboard between your screen and the surface, so sometimes you can short circuit, and what that looks like is a tablespoon of milky white substrate starts leaking out around the casing. You pretty quickly just pick that up with a sorbent rag and cut your injections. So that was one of the real challenges that we had, and we tried to overcome that really just by putting more substrate in other areas, i.e. other injection wells. There was one well that really took a lot of substrate. So we're like, okay, this is an area that's right where weathered rock exists. Let's put more substrate in there. Any other things you can think of, Hannah?
No, I think that was the big highlights. Yeah.
And then Julian, hi Julian, were there any unexpected or surprising results during the pilot test? I guess we sort of knew that top of the rock was going to be variable, but being so shallow in certain areas, that was a bit of a surprise. Anything you
I
can
would
think
say
of, Hannah?
too, we weren't sure if we would impact the bedrock at all. So seeing that there were large decreases in our CVOCs at the fractured rock well was maybe not totally a surprise, but was interesting to see.
Yeah, it was a pleasant surprise, I would say. Right, that was the point, but you don't know if you're going to have that connectivity. So that's the purpose of a pilot test. And then we got another one from Scott Pearson. What was the brand model of the Bluetooth pressure conductance transducer? So that's the Aquatrol 200. And I'm pretty agnostic for equipment. So I'm not saying that, a certain vendor is better than another vendor. These probes I've used and they've always been pretty good. They have the little conductivity window in them and they have the head pressure as well. So particularly when we're doing the tests, well, I guess either for the injection and or for the well fluid replacement test, you have that head as well as conductivity. So you can actually see the pressure front come through ahead of the conductivity breakthrough. So yeah, that's Scott, that's the Aquatrol 200.
All right, I think we'll wrap up there with some great questions. If anyone else has a question after today, you can reach out to Hannah or Jim directly. So our next webinar will be on October 8th, same time, leveraging advanced digital solutions for efficient soil remediation in public rights-of-way. This will be presented by Yoav Rappaport, Parker Wills, and Rob Cushing at the same time, 12:30 to 1:30 p.m. Eastern. A link to the form for PH credit was posted in the Q&A feature. If you have any issues downloading that form, please contact us. And if you missed any of the questions on that form, the recording of this webinar will be posted on our YouTube channel in the next few weeks. Thank you to everyone who joined us for today's webinar. We hope to see you again in October.